So the next thing for us to induce within magnetism is talking about magnetic flux. And so for starters, let's go back and remember what we said when we talked about electric flux. So we defined electric flux as a measure of how much an electric field flows through a particular surface. So here's some surface, happens to be a square, so side of length L times side of length L, and you can see the electric field lines here that are penetrating. And so the electric flux depends on three things. First one is the strength of the electric field. So basically, what is the magnitude of this vector on the surface? Two is the area of the surface. So you notice here that we've got something listed as the area vector. The area vector happens to be perpendicular to the surface, and it has a magnitude that's equal to what the area of this surface is. So the magnitude of this area vector is just the area of our surface. And then the third thing is, what's the relative orientation of the electric field in the surface? Notice we've got an angle, in this case we've labeled it phi, between these two vectors. So we can account for all this mathematically and say that the electric flux, which we give a capital phi with a subscript of E, so the electric flux is equal to the magnitude of the electric field times the magnitude of the area of the magnitude of the area vector, it's nothing more than the area of the surface, times the cosine of phi, which is just the cosine of the angle between those two vectors. So again, phi here is the angle between the electric field vector and the area vector, which is normal to the surface. If you want the maximum flux, well, you get the maximum flux if basically you were to rotate the surface so that the area vector lined up with the electric field vector. So the maximum flux occurs when the surface is perpendicular to the direction of the electric field, which means that the normal to the surface, that's the area vector, is parallel to the electric field. So that's how I maximize my flux, is that I make the surface itself perpendicular to the electric field so that the area vector lines up. I get the area vector and the electric field pointing in the same direction. Magnetic flux basically works exactly the same way. The only thing that's changing here is, instead of talking about an electric field, we talk about a magnetic field. So magnetic flux is a measure of how much a magnetic field flows through a particular surface. It depends on three things. The first thing it depends on is the strength of the magnetic field. It depends on the area of the surface, and it depends on the relative orientation of the magnetic field in the surface. So again, quantitatively, we're going to capture what we care about in terms of thinking about the magnetic flux in this equation. The strength of the magnetic field, the magnitude of the area vector, how big is the surface, and then the cosine of the angle between the magnetic field vector and the area vector. Again, if you want to maximize the magnetic flux, that's going to occur when the surface is perpendicular to the magnetic field, which means that you would tilt the right side of this surface up to line up the area vector pointed along the magnetic field. So that's when you're going to maximize the magnetic flux. So some other things about magnetic flux. Well, again, if I think about this equation, I can again use this to figure out the units. So I mean, it's going to have units of, the magnetic field has units of Tesla, area has units of meters squared, cosine phi is just a number. So the units for magnetic flux are Tesla meters squared, and we end up calling that a Weber. So this is another quantity that has its own special unit. So Webers is another name for our SI unit for magnetic flux. What we're going to see is that when we change the magnetic flux through some loop, it's going to induce an electromotive force which induces a current around the loop. So the first question is, what on earth is an EMF? Well, an EMF, which we're going to use this lowercase epsilon symbol for, it's not a force. It's really an induced potential difference. So an EMF is sort of misnamed It's a historical name, we still use it. But really an EMF is talking about a voltage. Right? So when you change the magnetic flux through some loop, that induces a potential difference. That induced potential difference will drive a current around the loop. That's where we're headed with this. So since this is how we calculate the magnetic flux, then this means there are three ways that you can change the magnetic flux through a loop. You can change the strength of the magnetic field, you can change the area of the loop, and you can change the relative orientation between the magnetic field and the loop. So there's basically three pieces here: magnetic field, magnitude of the area, relative orientation between those three things. And what we'll see when we talk about Faraday's law in the next video is that when you change the magnetic flux by changing one of those three things, then you're going to induce an EMF which will drive a current around the loop.